find the centre of mass, the centroid of this shape using this formula. And as you can see, there's an x squared here, there's a y squared there, so they've told us essentially what we need to do to make this thing work. I have a quarter circle, which is this guy. And so I know they're going to use x's and y's. I also know that A is actually the area of D. Right? And this guy here is D. So I'm not going to do any clever math. Isn't the area of this D, isn't it just a quarter circle? I don't need to calculate it, right? And a circle is pi radius squared. So this would be 1/4 pi, the radius squared. And since the radius is A, can I just put in 1/4 pi A squared? And you're quite happy where that came from, right? So we already know that guy. We have two distinctly different line integrals to do. So let's do x bar first. It's going to be 1 over the area, which we've just done, and forgot to put my 2 in, 1 over 2 times the area. It's going to be this guy, x squared dy. But that's going to become, oh, too late now, I've written that. I'll fix that the next time. The double integral of x squared. And how are we going to get this sorted out? Well, oops, r is going to go from 0 to a, and theta is going to go from 0 to pi upon 2. We're comfortable with that bit. And so theta is going to go from 0 to pi upon 2. R is going to go from 0 to a. And we're going to have to turn this guy into, oh, let's fix this guy. This is a half pi. A half gets you 2 on the top. Can I just do that, which is the simple version? Got him out of the way. I've got a double integral, and I need to, and I should have done this much earlier, I need to turn it into that double integral, right? Now, this fella just says x squared y. So you've got to think of it as 0 dx plus x squared dy. Does that make sense that you need both pieces? Now, why do I need both pieces? Because that's going to be p and that's going to be q. And so when I do this guy, why do I never remember which way around these are? dq by dx, dp by dy. Please tell me that's the right way around. Is it?
Pretty sure.
Good.
Oh, good. Darn it, if I just got a mental block. I always just say, I know it's P and Q, and I know you reverse them, but then I forget which one you reverse, or I forget which variable. But we got it. So that's this guy. This was a little bit too early. I should have waited a little bit longer. If you do this guy here with respect to x, you get 2x, but take that way guy, you get nothing. And so I guess right now it looks kind of superficially like that, doesn't it? Where this is going to be the region D. And now we know D happens to be a quarter of a circle, which means that we should turn it into polar. So it's at this point here I should have done the polar stuff. And 2 times x, which is going to be r cos theta. And instead of dx by dy, won't we do another r dr d theta? Are you comfortable about that guy being the dxy and this guy being the 2x? and these being the limits of integration that generate that. So, new page. X bar then is going to be 2 over pi a squared. The integral from theta is 0 to pi upon 2, and r equals 0. Why am I putting pi upon 2? R equals 0 to a. There we go. Of 2 r squared cosine theta dr d theta. Okay, that's beginning to look pretty. Let's bring that 2 out and make this 4. And separate them. So from 0 to pi upon 2 cosine theta, and from 0 to a of 2r squared dr. Is everything I've done look good so far? Any obvious mistakes? It would be nice to tell me. Everything look good?
The 2r squared didn't you do? Yeah.
Everything look good now? Which is why I ask people to check things for me. Right, let's continue this quest. Okay, that's going to be a sine theta evaluated at 0 and at pi upon 2. This is going to be 1/3 r cubed evaluated at 0 to a. So what have I got? 4 pi a squared. Oh, that's just 1 take away nothing. That's just 1. And this is 1/3 a cubed. Take away nothing. And some nice cancelling. And that cancels mostly with that. So I'm going to have 4a on the top and 3 pi on the bottom, which is the answer. So it worked. Anybody want to guess at y bar?
Would it be the same but negative?
You would expect that negative to generate something negative, but actually it's just the same. And if you think about it, since the answer is in there, doesn't it make sense that the centroid should both be positive? Right. So the negative that they add into the formula, I think it's to do with orientation, right? It's because it's clockwise or anti-clockwise, whatever one it is, and that's just to fix it. So symmetry can save you some time, can't it? If the shape is obviously symmetric and the formula is quite clearly at least symmetric. And this was for essentially just a function where the z value, right, the height would be 1, right? That's why that works. If you make it more difficult, if you make it a 3D shape, bad things happen. But this is 2D, so you're good. We're finished Green's theorem, right? Which basically says, if you want to do a line integral of a closed loop, don't you just turn it into a double integral of the area that's inside the closed loop? Right, that's what Green's theorem essentially says. So now we're on to our last section, which I've got maybe the right number. Matthew's got me guessing now if I've been numbering these things correctly. 16.6, curl, and divergence. And you'll have to bear with me for a few moments. This is going to take me a couple of minutes, so why don't you do your attendance right now? That way, you know, you don't need to waste a minute at the end. I'm hopefully finding this. I want to show you a video. Small video, short video. And I believe I've got it. And I'm just trying to find out where the heck it is. Still looking for it. And here it is. Good. Okay, now this may or may not work. Visually it will work, but I'm trying to see if I can make the sound work, and it's kind of hit and miss. So here goes.
Today, you and I are going to get
Can you
into
hear it?
divergence and curl.
This
To
is
make sure
fun.
we're all on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be three-dimensional, or even higher, we're just going to be looking at 2 dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon? What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And what can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow? These sorts of questions can be surprisingly helpful. For example, the ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field.
Shows you how important curl and div really is to
Here,
engineers.
take a look at this vector field and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field evaluated at all of those points that act like sources will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in 2-dimensional inputs and spits out 2-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative. And that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point, you also think about the fluid flow around it, but this time, you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom, but quick up top, resulting in a net clockwise influence. And really, true proper curl is a three-dimensional idea, one where you associate each point in 3D space with a new vector, character.
It goes on. Sorry. Right. Interesting video. I mean, for the engineers amongst you, we've been doing an awful lot of algebraic magic, but curl and div are algebraic magic to many of you because you're not going to become engineers. But it's nice to know that you're actually going to do stuff with them, right? I think it's quite interesting to see what curl is basically is a measure of how much rotation is happening at a point in space and whether it's a positive or a negative. And the bigger the curl is, the faster the little thing would turn, right? So the size is also important. And that thing about sinks, right, where things go in and go out, to me, that makes me think of black holes, right? Things are coming in. But there is a theory that says there's white holes, which is there might be points in the universe where matter is just appearing out of nowhere and spurting out. Dylan, do you have a question? Or just
Nope.
Cool? Cool stuff, right? So now that I've given you, I don't know, hopefully a little insight to what these things are, wouldn't you like to know how to calculate them? Because that's essentially what this section is going to be about. And oh, I don't think I'm on the thing here. I'm still on the other thing. Get my answers up. Curl of a vector field. And the div of a vector field. The div is an easy one to calculate, and I should have put in who F is. We're doing a 3 or a 2. We're doing a 3. Okay. Imagine your vector field or vector function is three-dimensional, right? P, Q, and R. P, Q, and R are functions of X, Y, and Z, right? So an example might be X squared plus Y, XZ, right? That would be an example of a vector field, a 3D one. And if you want to find what the div is, you find the derivative with respect to X of P, the derivative with respect to Y of Q, and the derivative with respect to Z of R, which is one of the reasons I keep getting that other guy mixed up. Right, so in this case, you'd get 1 plus 1 plus X. So the answer would be, in this case, 2 plus X. Would you agree calculating the div is really just finding the partial derivative with X, Y, and Z and adding them together? Right. pretty easy to do. The curl, on the other hand, is not so nice. The curl is described as the cross product of this guy with that fella. So we're going to do a cross product. So let's set this thing up. Curl of F. Since it's the same as this guy, you might think, how's this going to work? Well, in a very strange way. If you only write that down, we call that the grad or the gradient operator. It's equal to this guy, and this guy. And you notice that there's nothing here. So this guy is d by dx, this guy is d by dy, and this guy is d by dz. And only the d's, only the operation gets written. And F is your friend P, Q, and R. So this is, I think, the first time we've ever actually did an operator. Oh, by the way, there's another way of describing the divergence. It's the dot product of the operator with F. So if I write this guy as d by dx, comma, d by dy, comma, d by dz, and if I call this guy P, Q, and R, the way an operator works is it might look like you're multiplying, but you're really combining. So d by dx with this guy, when you combine them, don't you get that guy? Plus this guy combined with that gets you that guy. And this operator combined with that, oops, you already did that, gets you that. And we go with the operator idea that it's not really a multiplication. When you do things, instead of thinking this times that, think of this operating on that, right? I wish I hadn't put that there, but too late now. In our question, it's going to be I, J, K, the grad operator, d by dy, dz, and P is going to be x, and Q is going to be x squared plus y, and z is going to be xz. Are you comfortable with how you set up? Top row is I, J, K all the time, right? Middle row is going to be the operator, and the bottom row is going to be F, P, Q, and R, right? P, Q, and R. And here goes. So many I's, take away so many J's, plus so many K's. Can you remember from Calc 3 how to calculate gradients? So to get the I guy, cover up those two. There's a little 2 by 2 matrix left behind. Major diagonal, take away minor diagonal. Okay, major diagonal is the derivative of this with respect to y, which is 0. Take away minor diagonal, which is the derivative of this with respect to z, which is also 0. Middle one. Major diagonal is this guy with respect to x, which gets me z. Take away this guy with respect to z, which gets me 0. Last one. This guy with respect to x gets me 2x. This guy with respect to y gets me 0. And so I end up with 0, negative z, and 2x. And there is your curl of f. So in one of them, you're basically just going to, I would probably use this formula because it's easy to remember. Find the partial derivative of p, q, and r with respect to x, y, and z, and then add them up. And in the curl one, you're going to do a lot of work, right? Because you've got to do all this stuff. Any questions? Okay. Now, if I plugged in a coordinate, for instance, if I did, let's put them together and try out and find some sinks and holes and spontaneous guys, right? So the divergence of f ended up being 2 plus x. And the curl of f, which we just calculated, ends up being 0, -7, and 2x. I'm interested in what's happening at the point 1, 1, 3, and I'm also interested in what's happening at the point 2, 5, -7. If I calculate the divergence of f at that point, you get 2 plus 3, which is 5. Now, since that's a positive number, at that point in space, wouldn't there be more stuff leaving it than coming in? Right, you know, spewing out more than is coming in. Now, if I did it on this point, you would get, well, they don't actually matter. All you get is that guy. So at that point in space, so can you imagine that this was my first one, right? Let's call this Q, and this is my Q. At this point here, since it is positive, there is more stuff going that way and less stuff going that way, right? So net effect is more stuff is leaving than entering. And here, more stuff is coming in than is leaving.
Mr.
Now, if you,
Robinson,
yes.
why is the first divergence of f5 and not 3?
Because it's 2 plus the x coordinate. So 2 plus 3 is 5.
Wouldn't it be 2 plus 1?
Oh, shooting space. Okay. I'm not changing my question. There, there it works. I don't know, getting old. Now, if you calculated the curl, you get a vector. And that vector, I'm not quite sure how a vector tells you how it's rotating, but if you imagine that happens to be the curl, what's that tell me about all the vectors that are going on? Evidently, if that was the curl, it's telling you in some way how that rotation is working, but I don't know how. Take me to a question. I gave you a nice easy one to make my life easy. Let's jump right in with a realistic one. Here is our vector field. It's x squared, y squared, z squared. So there's a lot going on here. It's x squared, y, z squared. And then it's x squared, y squared, z. Would you agree this vector field has some kind of symmetry going on? Does it look to you? It looks to me like there's some type of symmetry going on. So I want to find the divergence of it. And I'm just going to use this formula because it's, as I said, to me at least, it's easier to remember. And your P, your Q, and your R. So if you differentiate this guy with respect to x, you get 2x y squared z squared. If you differentiate this guy with respect to y, I believe you get x squared z squared. And is that an x squared? Oh, shooting space. That is an X. And if you do that one with respect to get, you get X squared, Y squared. So kind of symmetry in the answer. Is there anything I can do to make this pretty? Well, I could take those two guys and pull out a Z squared. Not worth it. That's as pretty as the answer is going to get. The curl of F. I have I have J, I have K. I'll put the grad operator in. D by dx, d by dy, d by dz. And then I'll do my P, which is x, y squared, z squared. My Q, which is x squared, y, z squared. And my R, which is x squared, y squared, z. And then it's going to be so many i's, take away so many j's, plus so many k's. So watch out for mistakes. Okay, if you differentiate this guy with respect to y, you get 2x squared y z minus, if you differentiate this fella here with respect to z, you get 2x squared y z, which is 0. Oh, I kind of like that. And you do this one. Differentiate this guy with respect to x, and you get 2x y squared z. Take away 2x y squared z, which is 0. I think I know what the next one is. Differentiate this guy, and you get 2x y z squared. And if you go this way, you get take away 2x y z squared, which is also 0. And so this ends up being the 0 vector. What kind of vector field do you have when the curl is the 0 vector? Any ideas? What kind of vector field do you have if the curl is the 0 vector?
This is just a guess, but would it be like a uniform vector field or something?
It's got a name, and that uniform's kind of interesting, the one you just did. It's actually our old friend, the conservative field. I think I remember mentioning that you don't want to prove something's a conservative field when it's 3 dimensions because of how ugly it is. Would you agree it's pretty ugly to just prove that it's a conservative field? But that's what it is. Conservative fields are really useful because in that little video, it seems that the people in physics need the field to be conservative for it to be fluid flow, right? So if you're modeling anything to do with liquids moving places, right, the vector field that's doing that has to be a conservative field, or the thing can't exist in real life. Evidently, that's important to them. Let's do a baby one. I'm not even going to tell you who he is. I'm doing a 2-dimensional one. Right. And let's get the curl. So it's going to be essentially I and J, but you don't really need the I and J when it's a 2-dimensional. All you need to do is take these two guys and do a P and do a Q. and you get that guy. Take away that guy. You agree that's the only guy that's left? I mean, I could stick an I and a j, but that wouldn't really help in these questions. When it's 2 by 2, you don't need them. If this guy is 0, what kind of vector field do we have? What kind of vector field do you have if this is 0? You have a conservative vector field. And can you remember the test? Well, if you rearrange that guy, isn't that the test that you use for a 2-dimensional vector field to see if it's conservative or not? Do you see how it works? Now, I'm not going to even attempt to do it, but can you imagine a 4th-dimensional vector field? I, j, k, l, 4 operators, maybe the last one dt. There'd be a p, q, an r, and an s in your vector field. You would do this whole calculation, only once you go to 3 or 4, won't you get a vector? And if you got a 0 vector, you are talking about a conservative field. So those guys in astrophysics who deal with space-time, which is basically 4-dimensional reality, if they are interested in dealing with things, it wouldn't surprise me if the universe was a conservative field. It would be nice if it was, at least, because I'm sure the math would be much easier to deal with. How are we doing, guys? If you're not a physics person, isn't it just 2 formulas that you apply and you get 2 answers? One's a div and the other's a curl. And if you're a physics kind of guy, you can say, well, I might be able to use that in fluid dynamics. Yeah, we got one last one to do. And do I want 2? Do I want 3? I want 2, I think. So we're doing a 9xy e to the z, 0, which I kind of like, and a y z e to the x. And I'm going to do the div first. So P, Q, no. So differentiate with respect to x, differentiate that one with y, and differentiate that one with z. Now, if you do this with x, you get 9y e to the z. That guy's obviously nothing. And if you do this one with z, you get y e to the x. And so nothing really much to do except that's the answer. We're finished. Do the curl now. We have I, we have j, we have k. We have our operators. And we have p. We have q. And we have r. So it's going to be so many i's. Take away so many j's. Plus so many k's. Put that one there. Put that one there. Let's see what we get. If you differentiate this expression with respect to y, you get z e to the x, take away nothing. If you do the middle one, differentiate this with respect to x, you get y z e to the x, take away, if you differentiate this with respect to z, you get 9xy e to the z. And then for the last one, the k guy, That gets you 0. Take away, if you differentiate this guy with respect to y, you get 9x e to the z. And so we get that guy. That's messy. Negative and negative make that negative. So I'll put this guy first. Take away that one. It just kind of looks prettier. And this one. So if you're not an engineer, you can still get curls and divs, can't you? You just need to apply the process. This is really a formula, and isn't this more a process? Looking good? Oh, I just looked at the answer. I guess you could have pulled out a common factor. Why I didn't notice it. And the other answer is right. So we're good. You've already, I think, done your last name, but in case you missed doing that, will you say your last name and bye-bye for now? And I'll see you tomorrow, where we have got lots of practice at finding curls and divs. It's a biggie, so I'll spend as much time as I can doing as many situations as we can. Bye-bye, guys. Do you like curls and divs, Maggie?
Yeah, they seem pretty interesting. Can I see the sheet where you did the example P and Q?
The P and Q one? Sure. When you do it as a two-dimensional, what you end up with is the... There we go. There we got it. I'll put it on the screen. So you had to adapt it, because when you do a 2x2 matrix, you don't need the i's and j's. Here we go. So you do the operator, and you do just P and Q. And that guy, take away that guy, because there's only one of them, right? And so you differentiate this guy with x, and you take away this guy with y. And if it's equal to 0, you have a conservative field.
Okay.
So that's where the test for are you a conservative field came from. It came from this has to be true. Now, if you want to do a conservative field for three-dimensional, you actually have to calculate the curl, and it needs to be equal to the 0 vector. And if it is, you've got a conservative field. It's probably a lot harder to be a conservative field in 3D than it is to be a conservative field in 2D.